The thing that's most interesting about this is the production system. It's a level of production technology that is far in advance of any automotive plant on Earth.
By the end of 2025, Tesla's Fremont production line still relied on more than 1,000 welding, painting, and assembly robots across the factory. But as 2026 began, Tesla removed half of the robotic arms from its production line. And Elon Musk confidently claimed that Tesla now has a vehicle manufacturing system unlike anything else in the world. A massive number of robots have been eliminated and replaced with a proprietary technology, a next-generation machine that Elon Musk spent years developing. Yes, it's none other than the fourth-generation Giga Press, built specifically to manufacture Tesla's upcoming vehicles, including the Cybercab robotaxi. This machine is designed to deliver the highest casting capacity ever achieved while operating at speeds more like an electronics assembly line than a traditional automotive factory, making it ideal for producing compact vehicles. That raises an obvious question. Why would Tesla need an even larger Giga Press to build smaller cars? What exactly is Elon Musk's plan, and what advantages does this new machine give Tesla? Over the next 10 minutes, you'll discover the entire bold strategy that the world's richest man is preparing to put into action. If you think the Giga Press is just another oversized factory machine, you're missing the invention that's quietly changing how cars are built forever. This isn't simply bigger equipment, it's the manufacturing breakthrough that gave Tesla an edge the rest of the auto industry is still struggling to catch. The story goes back to the development of the Model Y. Tesla had an ambitious vision: eliminate countless welded parts and replace them with a single massive aluminum casting. There was only one problem. The machine capable of doing it didn't really exist. Elon Musk searched the globe, reaching out to the world's leading die-casting manufacturers, hoping someone could build what Tesla needed. Every company came up short, except one. An Italian manufacturer named Idra had been secretly developing an enormous high-pressure die-casting machine. By an incredible stroke of timing, it was exactly the breakthrough Elon had been looking for. Today, that machine is known as the Giga Press, and it produces some of the largest structural components found in vehicles like the Model Y and the Cybertruck. Its process begins by melting aluminum alloy at extremely high temperatures inside a massive furnace. Once the metal reaches its molten state, it's injected into a precision-engineered steel mold shaped exactly like the vehicle component being produced. Then comes the most critical moment. The Giga Press forces the molten aluminum into every microscopic corner of the mold using extraordinary pressure, ensuring there are no gaps, no weak spots, and virtually no defects. As soon as the mold is completely filled, the cooling process begins, allowing the aluminum to solidify into its final form. But this is where precision becomes everything. Inject the metal too quickly and trapped air creates bubbles that weaken the part. Move too slowly, and the aluminum begins cooling before every section of the mold is filled, ruining the entire casting.
Metal's got to cool, and then you've got to automate, getting all the bits and pieces off the casting so it's usable.
That's why the cooling system is engineered to maintain an incredibly uniform temperature throughout the process, giving every finished component the strength, consistency, and dimensional accuracy Tesla demands. Once the casting is complete, robotic systems remove the part, trim away excess material, and send it through rigorous quality inspections before it ever reaches the assembly line. The result is far more than a faster manufacturing process. By replacing dozens of smaller welded pieces with a single giant casting, the Giga Press makes vehicles lighter, significantly stronger, and more rigid, while dramatically reducing production time, manufacturing complexity, and labor requirements, all with one revolutionary machine. Today, Gigacasting is no longer Tesla's exclusive advantage. Automakers around the world have begun racing to adopt the technology, with companies like General Motors, Hyundai, Volvo, Zeekr, and XPeng pouring billions into massive die-casting systems of their own. XPeng, for example, has already invested in a staggering 16,000-ton gigacasting machine. But while everyone else is trying to catch up, Tesla is preparing to leap so far ahead that the entire industry may have to rethink what's possible. Elon Musk's next target isn't 20,000 tons or even 30,000. It's an almost unbelievable 50,000-ton Giga Press.
Real fast. And then I guess maybe we need to just get even bigger casting machines. Sure, why not? Down, yeah, let's 50,000 tons.
When Elon first revealed that number, one question immediately came to mind. How could something that enormous even exist? Where could Tesla possibly fit a machine of that size? How long would it take to install? And perhaps the biggest mystery of all, how could a single press produce the structural components for 5 vehicles at the same time? It almost sounds impossible. But according to Elon Musk, that's exactly the point. Once the 50,000-ton Giga Press enters production, the factory won't just become faster, it will move at a pace humans simply can't match. Every stage of the process, from injecting molten aluminum and cooling the mold to removing the finished casting, will run in a fully automated sequence without interruption. Each production cycle is expected to take just 5 seconds, meaning an entire vehicle frame could be completed in less time than it takes you to blink a few times.
It doesn't look like a normal car manufacturing line. It looks like a really high-speed consumer electronics line. In fact, the line will move so fast that actually people can't even get close to it.
Now, you might assume a 50,000-ton Giga Press works completely differently from the 6,000 or 9,000-ton versions. Surprisingly, the core process remains remarkably similar. The real difference isn't the concept, it's the incredible scale and precision behind every single step. Everything starts with the aluminum. Tesla feeds both brand new aluminum ingots and recycled aluminum from previous castings into a furnace heated to roughly 850 degrees Celsius. Once the metal has completely melted, surface impurities are removed before the liquid aluminum travels through heated pipelines into a second sealed holding furnace, where it's kept between 750 and 850 degrees Celsius to ensure it's always ready for the next casting cycle. Based on what we know, Tesla relies on a dual furnace system. The first furnace, powered by natural gas, is responsible for melting the aluminum at around 850 degrees Celsius. The second is electrically heated and serves as a holding furnace, maintaining the molten alloy within that ideal 750 to 850 degree temperature range we mentioned earlier. But temperature alone isn't enough. The empty space inside the holding furnace is filled with nitrogen gas, preventing the molten aluminum from reacting with oxygen and forming unwanted oxides while also helping maintain a stable environment. To make the alloy even cleaner, operators use argon gas, a rotary degasser, and a silicon carbide filter to eliminate dissolved gases and remove particles larger than 25 microns. Only after all of that is the aluminum finally ready for the next stage, preparing the mold. Before every casting cycle begins, the Giga Press coats the mold with a thin layer of lubricant. A robotic arm sprays about 35 milliliters of soybean oil evenly across the mold surface, much like greasing a baking pan, so the finished part can be released cleanly afterward. The system then creates a vacuum to remove trapped air before molten aluminum flows from the holding furnace into the Giga Press's shot chamber. Finally, a high-speed piston, itself lubricated with roughly 8 milliliters of oil, before every shot, drives the molten aluminum into the mold cavity with tremendous force, setting the stage for the entire casting process. Once the molten aluminum has been injected, the waiting begins, but only for a moment. The metal remains inside the mold just long enough to solidify before the newly formed casting is released at an astonishing temperature of nearly 400 degrees Celsius. Even then, the process is far from over. The glowing hot casting is immediately transferred into a cooling bath, where its temperature plunges from roughly 400 degrees Celsius to about 50 degrees. That rapid cooling isn't just about speeding things up, it also helps eliminate certain casting defects while improving the material's overall mechanical properties. Meanwhile, the mold has its own reset sequence. After opening, it's cooled to around 185 degrees Celsius before a robotic system thoroughly cleans every surface, ensuring it's perfectly prepared for the next shot. Thanks to this highly synchronized process, another casting cycle can usually begin just 1 to 2 minutes after the previous one ends. Any excess aluminum left on the finished part is trimmed away and sent straight back into the melting process, minimizing waste. Before a casting is approved, it undergoes an X-ray inspection to verify its internal quality and structural integrity, making sure no hidden defects escape detection. But perhaps the greatest engineering challenge happens during the injection itself. Imagine forcing molten aluminum into a sealed mold under enormous pressure. Without enough clamping force, that mold could literally be forced apart. That's why the Giga Press must lock the two halves together with extraordinary strength. And when you're talking about Tesla's proposed 50,000-ton Giga Press, the amount of clamping force involved is nothing short of enormous. According to Elon Musk, achieving that kind of production speed isn't just about building a larger machine. It requires an entirely new manufacturing ecosystem. Tesla had to develop an ultra-fast cooling system, a highly intelligent mold release mechanism, and an AI-powered inspection process capable of verifying every casting in real time, a combination of technologies no automaker has ever attempted to integrate at this scale. And that's where the story becomes even more fascinating. The 50,000-ton Giga Press isn't simply redefining how cars are built. It represents a fundamental shift in how factories operate. For the first time, automotive manufacturing is beginning to resemble the world of consumer electronics, highly automated, incredibly fast, remarkably compact, and engineered to maximize every square foot of factory space. According to reports, Tesla has reduced the number of major structural components from roughly 200 in the Model Y to only around 80 in the Cybercab. That isn't simply an incremental manufacturing upgrade. It's a complete reinvention of how an automobile is designed from the ground up. For more than a century, cars have been built by joining together hundreds of separate pieces using welds, bolts, brackets, rivets, and countless connection points. The problem is that every one of those joints can eventually become a source of stress, fatigue, or long-term wear. Tesla is taking the exact opposite approach. Instead of building a vehicle piece by piece, the company wants much of the Cybercab structure to exist as one massive unified casting, transforming what used to be hundreds of individual components into a single mechanical system. The benefits extend far beyond simplifying production. A more unified structure delivers greater rigidity, eliminates countless potential failure points, and allows the chassis to behave much more like one continuous piece of metal rather than a collection of assembled parts. That translates into real-world advantages across the board, from improved ride comfort and sharper handling to more predictable crash energy management. And in a future where vehicles are expected to drive themselves, that level of structural consistency could become one of the most important engineering advantages of all. Just when it seems Tesla has reinvented the factory with the Giga Press, the company sets its sights on another manufacturing bottleneck, one that's been slowing down car production for decades: the paint shop. Painting a vehicle is one of the most expensive, energy-intensive, and time-consuming stages of the entire manufacturing process. So instead of making it faster, Tesla appears to be asking a far more radical question. What if the paint shop simply wasn't needed at all? According to Tesla patents, the Cybercab's body panels could be produced with color built directly into the material during the molding process. Rather than forming a panel first and then sending it through multiple painting stages, the finished color would emerge at the exact moment the panel is created. Interestingly, recent Cybercab production vehicles already appear noticeably glossier than the early matte finish prototypes, hinting that Tesla may be moving closer to making this concept a reality. If that's the case, the implications are enormous. Traditional paint shops occupy massive factory space, consume tremendous amounts of energy, and add both cost and complexity to every vehicle that rolls off the assembly line. Eliminate that entire step, and Tesla wouldn't just save time. It could fundamentally simplify manufacturing while dramatically lowering factory costs. Everyone may be wrong about the Tesla Cybercab. A total of 245 Tesla Cybercabs have just been spotted at Giga Texas, and that number could soon climb to 1,000 as Tesla's next-generation manufacturing platform begins to ramp up. Steering wheel-free Cybercabs have also started appearing in California, signaling that Tesla is gradually preparing for Cybercab robotaxis to replace the entire Model Y robotaxi fleet. With every new update, the Cybercab is becoming one of Tesla's most exciting vehicles to experience, while shattering the widespread belief that Tesla wouldn't be able to scale production of this model. There may be no greater driving experience than stepping into a car, having the doors close automatically behind you, watching the center display come to life, and then realizing there's no driver in front of you, no steering wheel, no accelerator, no brake pedal, no traditional controls that would allow an ordinary person to instantly take over. A few seconds later, the vehicle quietly pulls out of its parking space, watches for pedestrians, recognizes the traffic around it, chooses the best route, and takes you to your destination without a single human hand ever touching the controls. For years, that vision seemed like nothing more than one of Elon Musk's ambitious promises. But now, Tesla appears to be turning it into a real transportation system at Gigafactory, Texas. And what's happening with the Cybercab right now could genuinely shock you. A record-breaking 245 gold Tesla Cybercabs have just been spotted at Giga Texas in drone footage and aerial images, revealing hundreds of two-seat autonomous robotaxis lined up in neat rows. These vehicles are believed to be pre-production or testing units that were recently built inside the Texas factory, providing strong evidence that Tesla is rapidly accelerating production of its purpose-built self-driving vehicle. Previously, more than 100 Cybercabs had already been prepared to shuttle employees around the factory campus. But these are no longer just a handful of prototypes built for stage demonstrations or carefully controlled promotional videos. Tesla has assembled an entire fleet of vehicles with no steering wheels and no pedals, ready to perform repeated trips in a real-world operating environment. Eric, who leads Tesla's Cybercab and robotaxi engineering team, said he personally completed and logged around 50 rides in just a few days. That number may seem small compared to the millions of taxi trips made every day, but that's not the point. What makes it significant is that every one of those trips was carried out in a vehicle specifically designed to never require a human driver. Elon Musk has confirmed that Tesla plans to begin delivering the Cybercab to customers by the end of 2026 at a starting price of $30,000 or less. Even if that timeline slips into next year, it would still be an incredible achievement. At that price point, I believe the Cybercab would sell like hotcakes. Many companies would likely buy them to build their own robotaxi fleets and generate recurring revenue, making the long-term business opportunity enormous. Tesla Cybercabs have also been spotted being transported in San Bernardino, California. The vehicles were seen on flatbed trucks without steering wheels, suggesting that Tesla is actively preparing for the Cybercab's rollout in California. Tesla isn't simply testing another self-driving feature. The company is testing whether a car can completely eliminate the need for a human driver and still operate reliably as a full-scale transportation service. That's why the Cybercab shouldn't be viewed as just a smaller, cheaper Model 3 with the steering wheel removed. It is Tesla's first purpose-built robotaxi, developed on the company's next-generation vehicle platform, a completely new architecture designed from the ground up for affordable electric vehicles and large-scale autonomous transportation. This fundamental difference changes almost every aspect of how the vehicle is designed. A conventional car has to be built around a human driver. Automakers must include a steering wheel, pedals, a steering column, an instrument cluster, a gear selector, mirrors, warning systems, and countless mechanical components so a person can safely operate the vehicle. The Cybercab doesn't need most of those parts. By eliminating the driver, Tesla can also eliminate a significant number of components, wiring, structural supports, and potential points of failure. The result is a simpler cabin, a lighter vehicle, lower maintenance costs, and a manufacturing process that can be streamlined far more efficiently. According to specifications referenced in documents related to the vehicle, the Cybercab has a curb weight of approximately 3,113 pounds. That's roughly 700 to 750 pounds lighter than a standard Tesla Model 3, a substantial reduction for an electric vehicle. A lower curb weight means the vehicle requires less energy to accelerate, maintain speed, and repeatedly stop and start in urban traffic. It also allows Tesla to avoid installing an oversized battery pack simply to carry the extra weight of the battery itself, improving both efficiency and overall cost. The Cybercab is expected to use a battery pack of around 48 kilowatt hours, significantly smaller than those found in many of today's long-range electric vehicles. However, thanks to its lightweight design, aerodynamic body, and purpose-optimized drivetrain, the vehicle is still estimated to deliver a real-world driving range of approximately 290 to 300 miles. For an urban robotaxi, that may be the ideal balance. Instead of carrying an oversized and expensive battery pack that rarely gets fully utilized, the Cybercab has enough range to operate for hours before returning to recharge. This highlights one of the biggest differences between a personal vehicle and a purpose-built robotaxi. Private car buyers often want the longest possible driving range for peace of mind on occasional road trips, even though most of their daily driving covers only a few dozen kilometers. A robotaxi doesn't need that kind of emotional reassurance. It needs efficiency. It needs to know exactly when to recharge, when to stay on the road picking up passengers, and how to maximize the value of every kilowatt hour of electricity. The Cybercab appears to have been engineered around precisely that objective. Tesla says the Cybercab's drivetrain is capable of achieving an efficiency of at least 6.1 miles per kilowatt hour. Some test data even suggests energy consumption could be as low as around 165 watt-hours per mile under favorable conditions. If those figures hold up in real-world operation, the Cybercab could become one of the most energy-efficient electric vehicles ever mass-produced. Compared with the Model 3 and Model Y, its energy efficiency could be dramatically higher, potentially approaching twice as efficient in certain driving conditions. But the benefits of that efficiency go far beyond a lower electricity bill. In the robotaxi business, every watt-hour saved can translate directly into higher profits. A privately owned car is typically driven for only 1 or 2 hours a day, while a robotaxi could remain in service for 12, 16, or even more than 20 hours daily if charging, cleaning, and maintenance are managed efficiently. When even a small improvement in energy consumption is multiplied across hundreds of thousands of miles of operation, the resulting savings can become enormous. Another noteworthy detail is that the Cybercab is expected to feature a 219 horsepower electric motor driving the front wheels. That's a significant departure from many current Tesla models, which rely on rear-wheel drive or dual-motor all-wheel drive systems. A front-wheel drive layout can simplify the drivetrain, reduce the number of components, and free up additional rear cargo space. The Cybercab is also expected to have a payload capacity of around 617 pounds, enough for 2 passengers and their luggage. Inside, a massive 21-inch touchscreen, the largest ever fitted to a Tesla vehicle, serves as the command center for the entire robotaxi experience. Passengers can monitor the trip in real time, adjust the cabin temperature, unlock the doors, control entertainment features, and even instruct the vehicle to pull over and stop at any point during the ride. However, this is where an even more difficult question begins to emerge. What happens when a passenger steps into a Cybercab for the very first time and sees 2 empty seats, no driver, no steering wheel, and no visible sign that a human is in control? Tesla doesn't just have to make the Cybercab capable of driving safely on its own. It also has to convince millions of people that the vehicle is safe enough to trust their lives to an invisible software system. And that may be the Cybercab's greatest challenge. Tesla's hardware appears to be ready, with more than 100 vehicles already prepared at Gigafactory, Texas. But the deciding factor in whether the Cybercab can truly take to public streets is still the software. In a vehicle with no steering wheel and no pedals, full self-driving can't simply perform well most of the time. It has to be reliable enough to handle every aspect of every trip without requiring human supervision or intervention. That's why Tesla has begun letting employees ride in the Cybercab within the grounds of Gigafactory, Texas. Testing in a controlled internal environment allows the company to evaluate the vehicle under real-world conditions while maintaining a much higher level of oversight than would be possible on public roads. Tesla is also moving toward a more personalized version of full self-driving. After one Tesla owner complained that FSD frequently moved out of the fast lane and left the vehicle stuck in slower-moving traffic, Elon Musk said future versions of the system will remember specific user interventions. In other words, FSD could learn from the moments when drivers override its decisions and gradually adjust its behavior to better match their individual driving preferences. This could become an especially important feature for the Cybercab. Every passenger has a different idea of what makes for a comfortable ride. Some may prefer the vehicle to maintain a larger following distance and accelerate more gently, while others may prioritize the fastest route or want to minimize unnecessary lane changes. If those preferences are saved to a user's robotaxi account, passengers could enjoy a familiar and personalized experience every time they step into a Cybercab, even if it's a completely different vehicle. However, autonomous driving is only one piece of the robotaxi puzzle. A single Cybercab could transport dozens of passengers every day, which means its interior must remain clean and ready for the next ride at all times. To address this, Tesla is developing a system simply referred to in its documentation as the cleaning robot, equipped with a large robotic arm and an automatic tool-changing mechanism. The robot can switch between multiple attachments, including a vacuum nozzle, a debris-grabbing tool, and a microfiber cleaning module. It is designed to vacuum the cabin, pick up trash such as plastic bottles and aluminum cans, and retrieve personal belongings, like backpacks or other items that passengers may accidentally leave behind. The microfiber attachment is specifically designed to clean the Cybercab's 21-inch touchscreen, side windows, windshield, buttons, and door handles without scratching or damaging their surfaces, helping ensure the vehicle is ready for its next passenger with minimal human involvement. Forgotten belongings could also be automatically sorted by the robot into a designated lost and found compartment, rather than forcing the vehicle to remain out of service for an extended period. Tesla has previously indicated that passengers may even be charged an automatic cleaning fee if they leave excessive trash inside a robotaxi. The goal is to reduce cleaning costs while encouraging riders to keep the cabin tidy. Beyond its interior cleaning robot, Tesla is also developing automated vehicle wash stations that Cybercabs can drive through on their own. After completing a series of trips, the vehicle could autonomously travel to a service hub, receive an exterior wash, have its cabin cleaned, and then return to passenger service without human assistance. Tesla has also been granted a patent for a UV-based robotaxi sanitization system designed to disinfect the cabin between rides by eliminating bacteria and other microorganisms, further reducing turnaround time while maintaining a clean environment for passengers. Energy efficiency further strengthens the Cybercab's competitive advantage. Tesla expects the Cybercab to achieve at least 6.1 miles per kilowatt-hour, making it nearly twice as efficient as the Model 3 and Model Y under certain driving conditions. The company's 2025 impact report also states that full self-driving operates about 5% more efficiently than the average human driver. By combining optimized autonomous driving software with a lightweight body, a 48 kilowatt-hour battery pack, and Tesla's next-generation vehicle platform, the Cybercab could remain on the road longer while consuming significantly less energy. According to data published by Tesla, the Cybercab's greenhouse gas emissions per mile could be as little as 1/8 those of a conventional gasoline-powered vehicle. While electric vehicles still produce indirect emissions through electricity generation, those emissions are expected to continue declining as power grids incorporate a larger share of renewable energy sources such as solar and wind. Tesla is also reducing its environmental impact during the manufacturing process itself. The company's reaction injection molding process for the Cybercab's yellow body panels integrates color directly into the molding process, eliminating the need to send the vehicle through a traditional paint shop. According to Tesla, this approach cuts processing time from several hours to just a few minutes, reduces greenhouse gas emissions by roughly 35% across the supply chain and manufacturing process for the affected components, and completely eliminates volatile organic compound emissions associated with conventional automotive painting. This is what makes the Cybercab's next-generation vehicle platform so significant. Tesla isn't just removing the steering wheel and pedals, it's redesigning the entire vehicle by eliminating components, manufacturing steps, and operating costs that are no longer necessary for a purpose-built robotaxi.